is Unit 1, so we're in kinematics. Lesson number 6, acceleration due to gravity. Okay, so meaning things that are either falling in a gravitational field or even moving in a gravitational field. Even if it's moving up, it's still falling down. So let's start by taking a couple things. Usually I do this with much larger objects in the classroom. But let's say I had a pencil and an eraser. Okay, now the pencil is much lighter than the eraser. In class I usually do a pencil and a textbook. Actually I have a textbook right here. Textbook, pencil. So if I were to drop them, take a second to think for yourself how they would fall. Would one fall faster? 2, 1. Okay, you can rewatch that if it's a video in slow motion. But yeah, they fall at the same rate regardless of mass. One is heavier, and we'll talk more about forces in next unit. But the point is, Galileo did these experiments where he came across this idea that regardless of an object's mass, they fall at the same rate, the same acceleration. And this was even done in one of the Apollo missions. Can't remember which one. I want to say Apollo 12, but I'm not 100% sure. Where the astronauts on the moon, where there's no air resistance, dropped, I think, a hammer and a falcon feather. So a feather, right? And the hammer and the feather hit the ground at the exact same time. So the acceleration due to gravity on the Earth is a constant, and we know it to be right here at 9.81 meters per second squared down. Now this is a constant on Earth. It's not a constant everywhere in the universe. That value would be different if you were on the moon. If you're on the moon, it's actually 1/6 that amount. So there's a lot less gravity. If you're on Mars, it's 1/3 that amount. Okay, but it would be greater if you went to a heavier planet like Jupiter. Okay. Now, anything that is falling inside of a gravitational field or due to the influence of gravity, we say that that object is in free fall. And very important, they're only in free fall if they're falling only due to gravity. Right, so technically if there's air resistance, we don't really consider that free fall. But in a lot of situations, air resistance can be negligible, just not obviously with a falcon feather. But the falcon feather on the moon, dropping it would be free fall. Okay, now I also said if you throw something up, it can be moving up but still accelerating down. So remember we talked about if something's velocity and acceleration are in opposite direction, it just means the object is slowing down. So if I were to take this pen and throw it up, it would move up, but slow down until it reaches its peak, where it then changes direction, comes down, and speeds up. So we can actually draw this as a position time graph, where initially we go up. So initially we are going up, so our position is increasing. Notice the direction is up. But if you look at your tangents, which indicate your velocity at any one point, your tangents are decreasing. So that means we're slowing down until you get right to the peak where you would have a horizontal tangent. Now that would occur at one instant in time. And then you switch direction. You start coming down where your tangent is initially. Not a very steep slope, but the slope increases. So putting it all together, if you were to draw one position time graph for an object that you threw straight up in the air, it would look like this. And it comes back down. It would look nicer than that, but you get the idea. Okay. Oh, I had it right down here. It would look like this. Its velocity time graph initially being a large velocity up and finishing off at a large velocity down, where right at the peak where we change direction, your velocity is 0. So right at this peak here, you have a velocity of 0, but very, very important, your acceleration is not 0. It's still 9.81 meters per second squared down. Okay, so in this example, if a ball is moving up, it is still accelerating down. When it's at its maximum height, it's still accelerating down. It's not 0. It's always accelerating throughout that entire trajectory. Okay, so let's continue. And we'll try some sample problems. In this first question, we have a golf ball dropped from a height of 1.25 meters. How long does it take to reach the ground? So we can still use our equations for uniform acceleration, those 5 equations we learned the other day. And to find any piece of information, we need 3 other pieces of information. So it looks like in this question, they only give us 1, but there are 2 other pieces. But let's start with the obvious one. If we start it from a height here, and we drop it to the ground here, the displacement is going to be 1.25 meters down. If it's dropped, now here's where the other piece of information comes from. If it's dropped, meaning not thrown down or thrown up, just held like this, and then dropped. Right at that instant you let go, right, just before it actually starts moving down, well, its velocity is 0. So we know its initial velocity is 0. And lastly, since it's falling inside of a gravitational field, and it doesn't say this, but I'm assuming we're on Earth, right, our acceleration is equal to 9.81 meters per second squared down. So now we can solve for time. That's what we want to know, how long. So time is our unknown here. So we need the equation that does not have the variable for final velocity. So I believe that was from our sheet, the third equation. So I'll just go over here and continue writing, which was displacement equals initial velocity times time plus a half acceleration times time squared. And in this case, initial velocity is 0, so that whole term is going to become 0. Now remember, what we're going to do is we're going to use this coordinate system where up is positive. You could actually do it with where down is positive. It's your choice. But since we're just starting to learn this, we'll keep up as positive for now, which means displacement should be negative. So when I write it in, instead of writing 1.25 meters up, I'm just going to write negative 1.25. So our displacement is negative 1.25. And that equals 1/2 times acceleration, which is also down. So that would be negative 9.81 times time squared. And you can rearrange for time. So multiply both sides of the equation by 2. And then divide both sides by negative 9.8. And you'll get 2 times minus 1.25 divided by negative 9.81. Forgot my units here. And that equals time squared. Your negatives are actually going to cancel, which is a good thing, because I'm about to take the square root of both sides, and I don't want to have the square root of a negative number. So take the square root of both sides to solve for time. And you'll get time as, now when you take the square root of both sides, if you remember from math, You have two possible solutions. One's positive and one's negative. So you do the square root of 2 times 1.25 divided by 9.81 and 0.5. 0.50 seconds. So you have two options. It's either plus half a second or minus half a second. Minus half a second doesn't make a lot of sense. Now, it does make sense if you ignore the person. Okay, so you're starting watching this movie, if you will, at a point where the ball is right here. And half a second later, it's going to fall here. But if we didn't see the person, then you could probably predict that if you rewound the movie, that it would still come back down. Right? Because imagine throwing it up from the ground. It would have gone up, come to a stop, and come back down. Right? But in our case, we're not really worried about rewinding the movie, so we don't care about that negative value there. So we're just going to cancel it out, and we're going to say the time is 0.5 seconds. Okay, the second example says a clown throws a ball upwards. So the initial velocity, in this case, it's not 0. We have an initial velocity up of 10 meters per second. Now it's written as 10.00 because it's identifying this as 4 significant digits. And since it's falling inside of a gravitational field, or due to the influence of gravity, we know that the acceleration is 9.81 meters per second squared down. Now part A says, find the maximum height the ball reaches above its launch height. So there's more information right there where it says maximum height. So it's going to go up, and when it gets to its highest point, right before it changes direction and starts coming down, we know its velocity at that point is 0. Right? So equations really do tell a story. Right? So when you have an equation, right, and you say, okay, the final velocity is 0, then what we're doing is we're saying from this point where we threw it to this point where it reaches its maximum height. This may just look like me writing final velocity equals 0, but that has the information inside of it that that is its maximum height. And if I plug this into the equation, it's going to tell me what that actual maximum height is. So we have 1, 2, 3 known values and one unknown value, which is going to be displacement. And we want the equation that does not involve time. So our equation, let me just come over to the side a little bit, is V final squared equals V initial squared plus 2A delta D. So this equation we have to rearrange because we're solving for delta D here. So let's bring the initial velocity to the other side. So we have V final squared minus V initial squared equals 2A delta D. And then we'll divide both sides by 2A. And it has to be for both terms on the left side. So they cancel on the right. And we're left with delta D equals final minus initial, both squared, all divided by 2A. Now final velocity we said was 0, so that's actually going to cancel. Right? And we get 0 minus, so we're going to get a negative, our initial velocity being 10, and it's up, so we're going to leave it as positive. Remember, we'll make up positive. So minus 10 meters per second squared, all divided by 2 times a, which is down, so we're going to write that as negative. And we put that into our calculator. And get 5.10 meters. So this is a positive value. So that's telling you that our displacement is actually up. So it is 5.10 meters up, which makes sense since we're throwing a ball up and it reaches some maximum height. You would think our displacement would be up. It's always good when you look at your answer to ask yourself if that makes sense. Right? If you got a negative answer here, you should say, that doesn't make sense. If I threw a ball up, how can its maximum height be below where I threw it from? Right? And if you ask yourself those questions, then you could realize without going over your math that somewhere you made a mistake. So it's good to ask those types of questions when you look at your answer. So part B says find the time it takes to do so. So the time it takes to go from when the clown throws the ball up until its maximum height, which we solved to be 5.10 meters. So now that we actually have displacement, which is 5.10 meters, right, we can use any of those 5 equations that have time in it. Although it's probably best to use the one that doesn't have displacement in it, because then you're not introducing extra round off error from previous calculations. So in that case, we would use this one. It's our first one. So final velocity equals initial velocity plus a delta t. Final velocity is 0. And we can bring a delta t to the other side of the equation, so subtract it from both sides, and then divide both sides by negative a. And so you get time, right? Your negative a's will cancel, so you'll get time isolated there on the left side, which equals initial velocity, which we have as 10 meters per second, and it's positive. Divided by negative acceleration. So we have that negative sign, and then acceleration, I'm going to put in brackets. Acceleration is 9.81 meters per second squared down, or according to our coordinate system here, it's negative 9.81 meters per second. So we have a double negative there, which is good because that'll give us a positive value for time. Okay. So you put that into your calculator, so 10 divided by 9.81, you get 1.02 seconds. And that's your time.